Okay, everybody. So we started last time talking about the file systems, the chapter 4 of our textbook. It is the third most important topic about operating systems. That's what we said the last time. We said that in a computing environment, in a computer system, we need these things. Okay, we like to store very large amount of data somewhere, and we like this data to survive termination of processes, power outages, crashes of our system, and we like to manage this data such as access privileges, such as sharing of this data. And all of these requirements come together, and people found a new abstraction mechanism to solve these or to address these problems. They call that the file. Okay, so this is our new abstraction file. Along with processes, address spaces, the files are the third most important abstraction mechanisms that operating systems provide. And in this chapter, we are going to see what we are doing with the files and how we are doing those, what kind of approaches we have to solve the problems with the files. That's the topic of this chapter. So the processes are dead spaces. Now that we have the files. If you know these three, okay, if you know these three, then you started to really understand what an operating system is, how it works, why we are using operating systems. Okay, basically this is the abstraction of the file. Okay, the physically a file is a linear sequence of fixed size blocks. The block depends on the operating system, or it is maybe parameterized. We can say that a block could be a 1 kilobyte data, 4 kilobytes of data, and sometimes it is just 1 byte. Okay, so depending on your system, it can change, but this is as simple as this. Okay, if the operating system provides this kind of a abstraction for me, then I can do many things out of it. So you might say that, is it this simple? I mean, why are we talking about this? Is so simple? But remember, the address space was this simple too. Okay, what was address space? Each process has its own address space, and the address space starts from 0 to some large number. That was it. Okay, that was the definition of the address space. But it took us maybe 3 weeks to talk about all the details of these address spaces. So again, the file system is as simple as that, but we are going to see what kind of problems, the issues we have to address to get such a file definition. Okay, and with these, you need to find these kind of, you need to address these kind of problems. How do you find information on your file system? Okay, the thing is that each file is structured like this. Okay, and how do you find your file on your whole file system? And how do you find inside your file your information? And the second, how do you keep one user from reading other users' data? This is a multitasking system, right? Or maybe time-shared system. Many people are using the same file server. How do you provide protection for the users? And how do you manage all this data? How do you know which parts of your system is empty, which parts are not available? And how do you make this in an efficient way? So typical, maybe you might say that we kind of solve these problems with the memory, right? I mean, keeping one user from reading the other user's memory locations, like the memory protection, we already know that. And how do you know which memory blocks are free, which memory blocks are not free, and who owns them? These are all we have solved with the memory, the address spaces abstraction. That's what we know, but we are going to look at the same problem from a different perspective, because this time we are talking about the files, and the file technology and the memory technology are two different things. So we will not use exactly the same structure, and our problems are different actually. In usage of the memory, time was very critical. I mean, I cannot even spare a single cycle of memory, a single cycle of CPU to handle the memory. Remember what we did about the page replacement algorithms? All of them were like, I have to be efficient. I cannot do this and this and this and etc. When we do those kind of algorithms, we are not concerned that much about the CPU efficiency anymore, because files are stored on secondary storage, and secondary storage is already very slow compared to CPU and the memory. So it is okay to waste a few cycles of CPU time to do some file management stuff. So our algorithms will be a lot different than our memory management algorithms. Okay, so when you talk about your files and your file system, okay, you need to make some decisions, some design decisions, such as your file names. Each file has a name, so that you can access it later. But we don't have any process naming problems. Okay, each process is owned by somebody. Everybody knows what kind of processes they have. I start a process, I wait until it is terminated. Okay, so I am watching my process all the time. That's what I am doing. With the files, it is different. You create a file, and that file is supposed to go on until eternity, right? It is not supposed to be go away when the power goes off. So, and that means what? You will have lots of files, and I have to have a way of distinguishing the files from each other. How am I going to do that? I'm going to give names to the files, and those names will be, of course, has to be unique. Otherwise, there would be confusion between the files, and then that means that I have to be careful about these file names. So, file name structure is a design decision. Am I allowed to use the Turkish characters in file names? Am I allowed to use special characters like the ampersand sign or the question mark in my file name? Or my file names can be long, very long file names, like 1,000-character file names, and etc. You cannot expect to have okay, on a typical file system, especially on the file servers, you expect to have millions of files. So it doesn't make much sense to give them meaningful names for each file, because we don't have millions of words in Turkish, right? So giving unique file names in Turkish or in English is not an option. So maybe I should structure my file in a hierarchical way, such as my root directory, under the root directory, other directories, under the directories, I have such and such. So maybe I can solve this anarchy of having lots of files and file names in this kind of a structure, and we are going to talk about it. Access control is going to be important again. Who is reading what? Who is writing to what? What are the permissions about reading and writing? Versioning is important. I don't have to keep a single version of the file, the latest version. Maybe I am going to keep the other versions of the files. For example, I created a file, later somebody changed it, and somebody else changed it, and somebody else changed it. So the file has changed 5 times in the last year. For some reason, if I like to go back to the original file, maybe the file system should help me about that. And give me the file where it used to be like 1 year ago. So that's called versioning. Fault recovery is important. Well, I mean, since my files are residing on secondary storage, and secondary storage is supposed to be permanent, doesn't go away when the power is out. Okay, so what is fault recovery? Then fault recovery is this: if I am writing to my file, and during my writing the power goes away, the system crashes. So this means that I left my file in an unstable position. When I try to read it, it's not going to be the older version, it's not going to be the newer version, it's going to be something in between, and that's going to be a problem because that's a prematurely updated, not fully updated, or not fully stable file. That's called the fault recovery. We should have a way of recovering our data in case of system crashes. System crashes doesn't happen because there is a power outage when we are doing some critical stuff. It might happen because these secondary storage stuff, they are reliable, but they are not the most reliable thing. What is the, okay, question for you. What are the chances of you having a bit flop on a CPU? Am I connected to internet? No, because not. Okay. Bit flip or bit flop, okay, is the probability that a given bit on your memory will change from 0 to 1 or 1 to 0 randomly. You might say that, why is it happening? Well, it can happen because this is a physical stuff. It is electronics, and electronics, our CPUs, our memory are not perfect. Sometimes your bits change from 0 to 1, 1 to 0. It happens so rarely. Maybe the probability is 10 to the power minus 12. Okay. So every time, every second, there is a 10 to the ten to the power minus 12 chances of a bit changing from 0 to 1 in my memory. And it happens. It's happening right now. Okay, it is happening right now. So if that bit is a very critical bit, at most what it can do is, it might crash my operating system. And sometimes I get operating system crashes meaninglessly. It just my operating system just crashes. That's it. And nobody will send an email to Microsoft saying that, okay, this computer crashed in an unreasonable way. I was not doing anything. Well, it might happen, they say, okay? So because, operating systems contain lots of bugs. Usually they crash for reasons other than the bit flip or bit flop stuff, okay? The thing is that we just start them. But if we have such bit changes on my computer, and maybe I can say the same thing for the secondary storage too, but this becomes a problem for the secondary storage, because for the secondary storage, those bits are supposed to survive much longer, not just 1 hour, 2 hours, 3 hours. And I don't have the chances of restarting my computer for the secondary storage. Once the data is corrupted, it is corrupted, okay? So that fault recovery becomes important. Sometimes I start my computer, it doesn't start, I don't know what happened, but the data is corrupt. And if the data is at the critical position is corrupt, such as the boot sector, then I will be in trouble. There should be ways of doing this fault recovery. Am I not connected to internet? Okay, I am connected. So let me try to get this bit flip error. Okay. And memory. So there somebody is answering, how come the bit flips aren't destroying my computer? Because it is so rare. Makers ignore bit flip errors. And you know what people do? They get the ASCII table, okay? For example, no, not this one, this one, okay. Get rid of this one. Get rid of this one. Yeah. For example, youtube.com, right? they get each of these ASCII characters. For example, the ASCII character Y, the binary representation of Y, let's say, I am just assuming this, it is not of course correct. Okay, 8 bits, right? Let's say this is the binary character for Y, and they say that if I change this 0 to 1, it's going to be 1 0 0 1 1 0 0 0. So by chance, if on somebody's computer, if I change this 0 to Y, instead of this going to be Y, let's say it's going to be Z. So that means that somebody is going to ask ZooTube, right? Somebody is going to try to access the zootube.com because they bit change and they don't know. And if I register this name, internet name, if I register this internet name, if I own it, that person will think that he's going to access the YouTube, but it is going to actually, in fact, accessing ZooTube. Okay, they will not realize that they are accessing ZooTube, and then I can show them fake content. I can show them that they won the lottery. I can show them that there is this such and such fake news and etc. This is a very profitable business. Actually, of course, it is illegal, but it is profitable business, and they are taking advantage of this bit flap error. Read about it, okay? I was trying to get this memory error rate, okay, for the memories. Yeah. So research has shown that the computer with 4 gigabytes of memory has a 96 chance of having a random bit flip every 3 days. So every 3 days, my computer is, okay, somebody started it. Why don't I join it? Okay, so every 3 days, my computer is going to have this error. So there are billions of computers on this world, right? And if you multiply this with billions of computers, and if you multiply this number with the small computer like the IoT devices and everything, so this error is happening a lot of times, and I can take advantage of this error, you guys say. Okay, our point here is this: if this kind of an error is happening on my memory, this kind of stuff is happening on my hard drives too. Okay, so if the thing is that if my computer crashes because of this error, I restart it. For my file systems, there is no restarting. When you restart it, you end up at the same position. Your data has not changed. It is the same as the erroneous data. So fault recovery is something important. I have to do this. Previously, our only strategy for the faults, like the system crashes, just restarting the computer from the beginning. Now it is different. I have to take care of it. Would I be able to recover from all kinds of faults? No. That's why you take backups. Okay? That's why you take backups. In the memory world, in the CPU world, we never talked about taking backups of your processes. That would be too expensive, right? That would be too expensive. But in the data world, in the secondary storage world, yeah, this backup is important. If the things that you are doing are very, very critical, for example, you are on a spaceship, on a satellite, you are on a mission to Mars, and your computer is so important. Every bit what you are doing is important. So what you do, you run the same thing on 2 different computers synchronously. Okay, you are running the same procedure on 2 different computers on the same platform. Okay, and at the end of each procedure result, you compare the result if they are the same, to see if they are the same. Okay, if the things that you are doing is so important, then you do this. Obviously, this is very time wasting and it is very expensive. So you need 2 computers to do the same thing again. But if you need to do it, then you would do it that way. By the way, Getting this bit flip errors on space is much more frequent because you have the small particles coming from the sun or the other sources from the space, and those particles, they go through your chips actually, and some from time to time they damage your computer or they mess up your memory. So it happens more often in space. Okay, file operation with the design decision. What kind of file operations am I allowed to do, and many more stuff. So these are the design decisions for the files and file systems. Let's start from the file names. Okay. Again, the file is our new friend and our new abstraction mechanism, and it provides a way to store information on. Whenever I say disk, okay, take it as secondary storage. It doesn't have to be physical, cylindrical, or circular disks. Okay. Nowadays we are using SSDs, solid state drives, more than the disk, but still we are using the disk. Well, I mean, we are still using the tape drives. Okay. I mean, tapes. Remember the tapes? I showed you the tapes. They are from 60s. They are from 50s. We still use them to get our very, very old data. Still, I am going to, most of the time when I say disk, I don't mean that physical disk. It is the secondary storage. So it provides a way to store information on our disk and read back later. That's what we know, very, very simple definition. And each file needs to have a name. It changes from system to system. Some systems are, for the file names, they are case sensitive. For example, our best friend operating system is Unix. Unix is case sensitive. A file with like this file, file1.txt is different from file1.txt, right? For Windows, for DOS, it doesn't matter. Okay. For the Unix operating system, okay, the file system extensions, they are permitted, but they are not required. Okay. And most of the time they are uninterpreted. I mean, a C program is supposed to have an extension of C.C, but if I try to compile a TXT program, the GCC compiler will not object to it. It will try to compile it. So my C programs doesn't have to have .C extension. It is only for me, for the humans. It is not for the compilers or the operating system. Okay, so the extensions have different meanings depending on your file system. The lengths of the extensions are different. For the old MS-DOS file systems, the length could be at most 3 characters. For the newer ones, the length could be anything. In fact, the character dot doesn't mean anything for the Unix operating system. It is just as ordinary as the character A. The character set, am I allowed to use the Turkish characters in my file system? And most of them nowadays, yeah, they allow it. But just to be careful, sometimes if we are using some old software that cannot handle UTF-8 character set, I am not allowed, okay? And uniform, non-uniform file name scheme, and well, these are all design decisions on your file system. And the earlier systems, they say that, okay, for example, the MS-DOS file system, they say that my file names could be at most 8 characters, and I can allow at most 8 characters of extensions. Okay, so that would be it. That would be the whole thing. You cannot have any file names that are longer than 8 characters. An extension cannot be longer than 3 characters, and no non-ASCII characters. Everything has to be in ASCII characters. Small case, large case, the uppercase doesn't matter. Okay, I am not case sensitive. That was it. So if your design is like this, it is easy to satisfy all these design requirements. That's the design. But it will make my users' jobs a little bit difficult. I mean, if my file characters are like 8 characters at most, how am I supposed to say my project file for the latest version, etc. I like to have a longer file name. I cannot say that. Okay, so I need to make up lots of nonsense 8-character restricted file names. So my job as a user is difficult. Operating system job is easier. If you choose this path, then that's the trade-off. Usually we like to make our users feel relaxed. Choose any file name you like. I will handle the rest, including the Japanese characters, Arabic characters, Latin characters. Doesn't matter what kind of character set you use. I will make those kind of files, and the users feel they feel much better. Okay, and then we keep talking about the file systems. And let's try to define this file system. We have the files. We already know that. That's the definition of the file. Okay, abstraction mechanism. Provides a way to store information on the disk and read back later. It has a name, and with the names there are a set of rules for the file system, etc. But what's the file system? File system is this. File system is this. It's the file system is part of the operating system. That's one thing. Okay, like the memory management, like the CPU management, process management, thread management. That is part of the operating system. It is called file system. And depending on the operating system, of course, the file systems are different. Part of the operating system, they deal with the files, okay? And in this chapter, actually, we are talking about the file system. We made the definition of the files. What's the file system? File system decides how my files are stored on my secondary storage. How am I going to access them? What kind of operations are allowed on these files, and etc. Okay? So there are many file systems. Some of the earliest ones are this FAT16 file access table. Okay, FAT means file access table. 16 means that 16-bit. So you may have 2 to the power 16 blocks of data on your disk. Then they realize that this is too restrictive. We have very large disks, and I can have much more data than 2 to the power 16 blocks, even if it's a block is a 4 kilobyte. So they have invented this FAT32. Well, later we ran out of space for this FAT32s too. It was from the Windows 98 days, but still this one is a very popular, even today, very popular file system. Lots of mobile devices are using this one. For example, smart SD cards. You know those SD cards, right? You know them, right? Those are digital cards that you use in your these are your SD cards. Usually we use FAT32 file system on these kind of storage units. Why? It is not because it's a very sophisticated file system. It is because it's very simple. And these, for example, I can handle. Well, 2 gigabytes is too much, but I can handle 2 gigabytes easily with FAT32. Or usually with these kind of devices, especially the small ones, I am talking about data less than 1 gigabyte. Okay, so FAT32 is very popular with these kind of devices. Okay, so later, of course, when our disks got larger and our recovery requirements changed, they have invented these kind of file systems, NTFS. Okay, nowadays on Windows environment, most people prefer using this NTFS. It has proven to be very robust against crashes. It is recoverable. It is efficient. So it is basically the Windows NT's file system. Later, Microsoft worked on the work on the resiliency of the file system, recoverability of the file systems. They say that it doesn't matter when your system crashes. If your system crashes, I am going to recover your data, resilient file system. And nowadays, Microsoft Word is using this file system. And for the Unix and for the other operating systems, there are their own file systems too. That doesn't, when I say for Windows I have this and for Unix I have that. Well, that's true, but those file systems are actually portable. I can have, of course, a FAT32 file system on my Unix, on my Linux operating system, because remember those SD cards? I am using SD cards on my Linux operating system. That means what? My Linux operating system can use FAT32 file systems too. Because as I said, file system is part of the operating system. If I add one more file system to my operating system, then I will start using it immediately. No problems. Okay, good. Any questions so far? File naming changes from system to system, from environment to environment, but these are some of the typical file names, extensions, backup files, C files, GIF files, help files, HTML files, and etc. As I said before, for the Unix, these extensions are just for the humans, so that humans would know what kind of files they are. Doesn't matter what kind of extension it has on it. For example, this s.txt is a txt file. I can compile it. The compiler, well, what does it say? It looks like it's a special. Okay, let me see if it's a. Okay, that one, t.txt, gcc t.txt. It thinks that okay. I don't know what kind of format it has. I just trying to compile it. It cannot compile it, so it is giving me an error message. If I make it t.txt, okay, let's first look at this definition of these files. Okay, it says ASCII text. There's a command named file in Unix. When you say file t.txt, it will tell you what kind of file it is. And if I make it t.txt to t. For example, just made up name, okay, and what? Oh, okay, yeah. So it still says it's a ASCII text. Doesn't depend on your extension txt. It doesn't say. I don't know what kind of file is this dfg. What is this? I mean, so my point is, for Unix, extensions are not important. It is permitted, but our system is not dependent on the extension. Okay, did everybody sign it? You just came in, right? Okay. For some reason, I will let you sign it. Okay, so with the files, okay, file structures, how do I structure my files? With the files, our most popular way of structuring files is this. Okay, Unix and Windows, they say that a file is a randomly accessible, thank you. A file is a randomly accessible sequences of bytes. Okay, so that's the whole structure. That's the whole structure. Okay, so a file is like this, from 0 to some length of the file, and it's randomly accessible bytes. You may say that give me the byte number 25, and operating system will give you, or file system will give it to you. Okay, and give me the length of the file, it will give you the length of the file. So that the file is structured like this for Unix and Windows. But for older systems, a file simply meant this. Okay, it only makes sense. Okay, a file is a collection of images of punch cards. Remember the punch cards? Each punch card can hold, let's say, 200 characters or something. So each block can hold data contained in a punch card, and you only access these records, these blocks. Okay, so these are called blocks. They were sequences of records, blocks or records, and each record it corresponds to each record corresponds to a punch card. Okay, or sometimes printer lines. Each record corresponds to a printer line. A printer line is 80 columns. Okay, so 80 characters is a record. So a file is a collection of these records. In Unix and Windows, we are talking about the bytes. Okay, some page-oriented file systems, it is just page-size blocks, maybe 1 kilobyte blocks, or 4 kilobyte blocks, or 512 bytes of data, etc. So as I said before, Unix and Windows, they prefer representing your files this way. Okay, we don't use these kind of we don't use these kind of file systems anymore. That doesn't mean that they are not non-existent, because we have to support all data somehow. Those are available, but we don't prefer them much. Okay, and this is how the Unix and Windows does it. Okay, just a 1 byte addressable structure, like a memory, like regular address space in our memory. We already know that these are the records. And in earlier versions of the files, this is a record. Okay, this is a record. This is another record, and this is another record. And the records are stored like a B tree. You know B tree from the data structures course, right? So when you open a file is structured like that. If you like to find this record lamb, what are you going to do? You are going to scan the root node. Where is lamb? It is less than ant? No, it is less than fog. No, it is less than pig. Yes. So is it less than goat? No, it is less than lion. Yeah, I have it, and I found lamb. You know how the B tree works, right? So it is, a file is structured like that, and you might say that this is too restrictive. What if I don't have a key field or index field? Well, you are not going to use this file system then. But usually in those days, when you say a secondary storage for a company, for a bank, the secondary storage means that you keep your user data, you keep your customer data. As a bank, your customers have TC kimlik numarası for each, right? Your national identity number for each, and you keep this national identity number as your index. And what are you going to store other than your customer information, right? So you are looking for your customer information, and you get your customer information using this B3 structure. Okay, but again, we don't use these much. Well, I mean, if you like to try to use this kind of a file structure, then build this structure on top of this structure. That's what we do. But in Unix and Windows, we prefer this structure, byte ordering, a sequence of byte addressable data. That's our file structures. Okay, and then we have our file types. Many different file types. We are not listing all type of files here. Regular files are, as the name implies, they just contain regular user information. Directories are special files. They are files, but they contain the links of information about other files. Okay, are files for maintaining the structure of the file system. In a regular file, I have this byte ordering. Okay, byte number 0, byte number 1, byte number 2, etc. That's what I have. But in a directory file, I have the same structure, but inside the structure, it is specially designed. It would say that in this directory file, I have the other file names. I know where those files live on my disk. I know their properties, and I will give you all of those. So this file is a special file that contains information about the other files. Okay, so that's how we have our directory structure. And sometimes to make things a little bit easy for us, we have character special files or the block special files. We will not pay much attention to these kind of file types. Character special files are like, what do you do when you open a file in C? You open a file and you start reading it, right? Character special files, again, opened. When you start reading it, the data doesn't come from the disk or from the secondary storage. It comes from the, for example, it comes from the keyboard. It comes from the mouse. It comes from the network. When you try to read something, okay, you read the next character that the user punches in from the keyboard, okay? So how do you do the random access on the character special file? You don't do random access. You just read it sequentially, okay? That's called character special file for input. There are character special files for output, for example, the printers. Whatever you send to this file, it is not being written to disk, okay? It is being sent to the printer, and printer prints it out, okay? So this is a special file. It looks like you are treating your file like a printer or the network drive or the keyboard, and it works that way. So you don't have to use, other than the file open, file read, and file write commands to access these kind of devices. So it's a different way of abstracting those devices. Again, I will not talk much about these character special files or the block special files. Okay, again, the file types. We are still talking about these design decisions about the files. The file types, some systems say that it has to be the right extension. I am not going to, for example, MS-DOS computers, MS-DOS operating system, it says that if a file doesn't have an extension of .exe executable file, I am not going to run it. It has to have an extension of exe. Okay, that's the rule. For other systems, it doesn't matter. For Unix, I don't have a special extension for the executable file. Okay, I am simply not paying any attention to the extension, but that doesn't mean that Unix doesn't know what is runnable and what is not runnable. Okay, so Unix knows what is runnable by looking at the file itself. It says that if a file is an executable file, then at the beginning it has to have a magic number. I don't know what that magic number is, but it's a constant number. Okay, it is common to the whole file system, for whole operating system actually. Whenever I say to Unix, run this command for me, Unix opens that file and see if this magic number is the same as the runnable program magic number that it has. If it is, then it says that if it is, then the next record, the next field is going to be my code size, then my data size, then my BSS size. BSS is the uninitialized data. Then my symbol table size and my entry point. And my entry point will be the beginning of the text, for example. Entry point will be here. Since entry point is here, I know the text size, my data will be here. And then I know the other stuff and other stuff. So that's how an executable file is formatted in Unix environment. Of course, it's going to be different for the Windows environment, Windows file system, etc. Okay, so that's how this, remember this file command. When I say file, tell me about all of them. It says this is a Unicode text. These are all directories. This unit text, and these are all directories. An ASCII text, and this is a symbolic ASCII. So it knows how to interpret these files by looking at the contents of them, not just by looking at the extensions of them. Okay, so because each file has a different structure in it. This is the executable file. This is an archive file. Archives are used for storing long-term storage of the files. They are usually compressed, sometimes encrypted. Okay, And this is the structure for an archive file. And it says that in an archive file there would be an header, and inside this header you have the information about the data. After the header you have your data, then another header, then you have your data. Inside your header you have the module name, date, owner, prediction, and size. So by looking at the protection and size, by looking at this size, you know where the second object module starts. This is how the archive files are stored. And in archive files in Unix, I have the tape, you know, these kind of files, tar command, tape archive. Tape archive, that comes from the tapes actually, okay? When you say tape archive minus CVF, right? I am going to put all these txt files in this, okay. No, I did it wrong, right? I should give my tar, no, this way, yeah. It put all of those txt stuff to, where did I put it? I don't know where it put. You guys, it's minus cfv.txt, and where do you know, create all the files, all the txts. I forgot the, yeah, I think it happened. Yeah, so I have a tape archive file. When I say, yeah, it's a POSIX tar archive, tape archive, GNU, and it knows it, okay? So this file is structured like this, okay? So you can come up with your own file type, and you can give this kind of structure. And if you like it to be standardized, you open up your file structure, and everybody would know what kind of file you have, okay? So these are designed that way from the beginning. Okay, file accesses, you know about this actually from your C, C++, Java courses. A file could be accessed in a sequential order, the random access order. Well, I mean, this makes it very easy. This is my file structure. Starts from byte number 0 to the length of the file. And random access means that, do you guys remember the C command, C function to call to access a random byte number in a C file? You say that I like to access the byte number 2012. I like to access this one.
LC?
Yes, seek, lseek. You just give, okay, I think the file descriptor and the 2012, and it returns, it just moves your current pointer to your file to that position, seek. Okay, that's the random access files. I can do whatever I want. But not all files are random access files. Some files are sequential access files. You can only read the next one, or previous one. Okay. Okay, remember those character special files are sequential access files. You can only say next, not the fifth one or the other ones. These are the file access methods. You already know these. Okay, any questions so far? Maybe I didn't say anything new. I'm trying to make an introduction to this chapter. After that, we will start seeing some stuff that are related to the file systems. Yes.
What about zip and rar file types? Those are also
What kind of files, RAR?
Zip and rar. Those are also POSIX compatible?
I am not sure. How do I compress? Do I remember it? Okay. I think there was a compress. How do I compress a RAR tar file? Yeah, dot tar dot z. I don't. How do you compress a Unix? Compress? I don't. I think I don't have. I don't have compress on my thing. Yeah, maybe I can. If you use this command, yeah, it is a. I think it says a POSIX standard to it. I am not sure about the zip. Yeah, zip is patented. The zip format, zip way of compressing files is patented. That's why you don't have any POSIX standards for it, because it is patented. I cannot write without paying license fees open source software, so they don't support it from especially Linux side. But compress is there. If I install this compress, and if I ask my file utility to say what kind of it is, I probably it's going to say it's a compressed tar file, a GNU compatible. Okay, so it depends how you design your program, actually, the zip or the .z files. And whoever has designed this archive system, okay, I am designing my zip files like that. Okay, good. Any other questions? It looks like I am out of my time. Let's take 15 minutes of break. Let's be here around 11:40. Please open the windows while we are out. Arkadaşlar pencereleri açın ya. Benim lafımı dinleyin, yok mu bu sınıfta ya? Oraları açın ya. Hocam. Ya hala bana dekanlıktan neler diye şeyler geliyor. İnsanlar bana yazdım zaten, düşünmüyorum ne dönüyorum. Bu öğleden sonra ne? Ben şey böyle çok satıcı, çok alıcı öyle valla. Neydi o? Aldın ne böyle 6.000 liraya ev olur. Ama iyi işte. Hadi tamam. Ben hazır olur var orada. Eşyalara tak. Ben 5 lira etmem. Ha o dedin mi? Evet, eşyalar 6.000'e veriyordum. Evet. Bak ben bu eşya satın almayı kalksam da olur mu? 5-10 senem var benim. Vay ya bak. Ben geri utanırım abi bunu. Evet ya. Bir de sahibinden öyle şey falan diyor. Depozit 10.000'den istiyor. Normalde hani bak öteki boş, depozit 10 çıkıyor. Bu eşyalar 10 çıkıyor. Yani evet. Ya öyle söylüyoruz. Aramıyoruz ya. Seneye mi arıyorsun? Nerede oturuyorsun? İzmit'te oturuyorum. Buralarda değil. Ne kadar bakıyor?
Biraz kiralarım biliyorsun. Hala atıyorlar. Ama şey diye düşünüyorum ben. Yani sanki şu an çıksam bir sene sonra koymayacak gibi. Böyle bir enflasyon var.
Part-time gibi de
Çalışmıyorsam
sıkıntı.
part-time
Mülakata
girersen
girdim.
nereye
Kabul
gidiyorsun?
ettiler. Kesinlikle CSE. Stajımı stajım sonra part-time çalışacağım. Onu da kabul ettim.
Stajda zaman bitiyor. Yazın mı?
İşte Temmuz'da biter. Temmuz, onu zaten yapacağım ama haftaya işte gelmemi istiyorum.
Şeyi bulabilirsin. Gelmemeli. Ama sen
İşte
stajı
bence
bir çıkar
bekletme.
aradan ondan sonra işte ücrete göre düşünüyorsun. Ben mesela staj yaparken başka iş bulmuştum. Çıktım direkt staj bitince. O iş.
Benim de Temmuz'da bitiyor sözleşme, onu bakıyorum artık.
Sıfırda yükseldim.
İlk günümden itibaren bakmaya başladım. Hiç boşu çarpmıyor.
Ben şu an
Staj daha da mülakat yok mu onları bekliyorum. Hemen cevap vermiyorum. Kabul ettiler. Ben de hemen kabul etmedim. Biraz geçtim. Ona göre.
Bayramı şey yapsınlar. Onu da var.
Burası çok güzel olur.
Daha bayramın günü benim iş günüme denk gelir.
Abi salak mı bu ya? Kesin bir dolandırıcılık var bu işte. O 125 metrekare bile. 4. kata bir şey de değil.
Hiçbir şey yok mesela. Başta ben
Şeye falan bak. Abla var lan hepsi. Utandı da oraya böyle dalmışlar biliyor musun? Fazla çakamadım. Şey o diğer sokak mahallelerde yani. Ümit evler. Ümit evler de çok ev var. Orası kentsel dönüşme gibi bir şey. O söylüyor.
Çok şeyi gördüm, hoca gördüm.
Değil başlangıç.
Adam var. Ben
Hava da var.
Ben şey diyorum zaten. Aklıma ilk de sıfır almışlar. Rekabet olmayan şey dedi. Programın çalışmadı. Yani bir şey
herhangi bir şey yok. Mesela
İster her şey yani.
her şey yapılması lazım.
Yani %100 ödemesi.
Bize işte
Balon falan. Yok işine mallı.
ama bizde şey yapmıyoruz mesela yani. Atıyorum regex yazdığı bir şey istiyoruz işte. Atıyorum 5 tane regex var. Ona göre puanları
Şey, ben de öyle ortamda bulunuyorum. Söylediği yapanlar falan. Ben
bir şey oluyor diye. Aslında o söylediği gibi değişik bir şey var.
o zaman muhtemelen sonra çok şeyde kalp var. Söylediği kalp dedi. Z'de çünkü ben Z'de
Şey çok sıkıntı ya. Onu açmam lazım.
Aynen.
Açtığım zaman sayfa falan yaparsın.
Çocuklara yoğun chat. Baktım bir tane çalışıyor. Sorun çöküyor tamam mı? Şey bekliyor, çocuğu bekliyor.
Soket yok yani. Abi soket yok. Ben Öyle anladın mı? Filan anlatacak. Öyle bir yavaşça.
Adamı kitap veriyorlar.
Bu adam 40 yazdım şeyi. Bütün pencerede çıkalım şöyle. 6 dakika olmuş. Çok şey. Sen bir mail yaptın.
Nerede lazım olmuş? Gerçek şey mi? Ama fena değil. Telefona falan bakma. Şuna bak ya.
Tamam sen çekecek. Risk alabilir miyim? İşte yani. Görüşürüz.
Ben maraton benim gibi böyle
Ben yıllarda ondan ama yani devlet şimdi sınavlar da çok düşük oluyor. Sınavdan sonra. O çalışırsa yani değişti. Adamlar kitapın dersi yayınlanıyor. Sonra da çok soru var. Yani falan gidince ekonomi dersi. Liberalizasyon alanının babası için. Bunun hangisi geleceğini savunması. Yani millet ben söylüyorum. CSE yalan birkaç ders var. Muhasebe defterin şekli var. Ona göre diyor ki hangisi büyük hangisi çıkıyor. Peki 500 lira kirasını verdi. 500 lira kira aldı bir yerden. Bunun şirket defterine nasıl yazdıysa. Çok şey yani.
Derslere girmiyor.
Yok. Zaten ders yok.
Kayıtları var.
Ama ders yapıyor da işte. O zaman ne olmadı? Ben şey yapmıştım. Sırada var.
Dersin ortasında çıkman gerekecek de imza attım ama geçen dersin. Onu sileyim mi yoksa?
Yok. Şu tarafa otur o zaman. Çıkacaksın oraya otur. Okay, so file access, we looked at this topic. Let's look at the file attributes. File attributes are usually they are called data about data. So I have let me clear this from the last semester stuff. Okay. So we have about the file, we have the name of the file. That's data about the file, okay? So the file contains some data, and the file name is some information about that data. Other than the file name, we have other known things about the data. It's called attributes, okay? Other information with each file is called attribute, or sometimes it is called metadata. Okay, so data about data is metadata, and depending on the operating system or the file system, we have different types of attributes, but the most important file attribute is your file name. Okay, without the file name, it would be very difficult to find your files, and it will be difficult to manipulate them. Other than the file names, these are some file attributes. For example, the protection. What kind of protection properties set I have on my file? You know, for the s.txt, it says that read, write, no execute for the owner, read for the group, no write, no execute for the group, and only for read for the others, execute and write, no, it is not set for the others. So for the Unix operating system, that's how we set the permissions for the files. We have three fields: the user field, group field, and the others field. For each one, I have the read, write, execute bits. So that's the protection for the Unix environment. For the Windows environment, you just open a, for example, here, let me just open a, on my desktop, I have a PNG file. Let me try to, when you say open up the properties, özellikler in Turkish, it opens it up. Okay, I have the file name, of course, and what kind of other things, for example, the creation time, the modification time, the access time, they are all file attributes. For the protection, for the security, you see, for the system, for the user, for the administrator, I have different modification, execution, reading, writing, and special privileges. And if I like to change these privileges, I can just say modify it, and I can take away all of my privileges, okay, or my privileges, and I change it that way. So this is how we change the privileges or the protection of the files in Windows environment. Changes from operating system to operating system. For the Unix, that's how we list it, but how chmod is the command utility for changing the access modes of a file. When you say, well, you see, I have three things. Okay, I have user, group, and other. For the user, I have read, write, execute. For the group, read, write, execute, read, write, execute. If they are all set, these bits are all 111. So 111 is 7, right? And 7 and 7. Okay, so I have 777 as the protection mode for a file, and I can change it that way. Chmod 0777 s.txt. If I show it again, see, it is all read, write, execute for all of them. Okay, if I like to set only the write or only the read fields, I would say 444. Okay, as you see, these are all 4. Or I change just 400. Only I am going to read it. Nobody is going to read it or execute the write to it. As you see, only I am permitted to it. Okay, so this is how you change your permissions or your protection for your Unix files. For the Windows, it is, I have the graphical user interface, I can change them. And some files are password protected. It would be if it is password protected, you would have a password attribute. The creator who created the file, the owner who owns the file. The creator and the owner are two different things. It looks like this one is created by myself and it is owned by myself. Creator and owner are the same person, but I can change ch own, ch. Oh, okay, it is order. Yes, ch owner. Then you would give the file name and the owner name. I can change the owner of the file. Okay, so it is possible. So read-only flag is, I mean, sometimes the files are read-only. You are not supposed to be writing to them. You might say that for the Unix, I can handle this with the protection fields. Yes, that's true. But for the other operating system, maybe this is required. Hidden flag if the file is hidden. If the file is a system file, it's an archive file, it's a binary file. For the Unix operating system, these are all, I mean, we don't use them. If a file is hidden, how do you represent a hidden file in Unix? How do you represent a hidden file in Unix? Do you know that? If a file starts with dot, okay, it is supposed to be a hidden file. When you say ls, I don't see any files that starts with an dot, but when I say ll, see, all of them, the ones that are starting with this dot, they are all hidden. Now I can see them. So ls minus l means that show me everything. No. ls means show me everything. ls minus a means show me all of them. When you say ls minus a, see, it shows you dot local, dot bash rc, and etc. These are hidden files. In Windows, of course, it is different. You open up the graphical user interface dialog and you say that this file is hidden. Okay, hidden files are usually not meant for the ordinary end users. Okay, so you kind of try to don't use these files. These are for my internal usage only. Regular end users are not supposed to reach these files, so I'm going to hide them. But since they are my files, I can access them the way I want. If you like, you can access them too. So hidden files, system files, archive files, ASCII files, we don't represent them, or random files, we don't represent them. For the temporary flag, okay, in Unix again, our temporary files are stored in a special directory called /tmt. Other than that, we don't do that. Okay, so record length, or the length of the file, is something, a property. See, when I say give me all those files using this command ls minus l, it gives me all these lengths. Okay, and these are bytes, and I think there is a way of saying ls minus lk, give me those sizes in kilobytes. I guess maybe I am not right. It gave me the same thing. I don't remember what that. Okay. Almost all columns directory died. I have to remember it. Hyperlink hide. Yeah, minus K default. How come I didn't get minus K, right? I don't know what happened there. Minus LK. How about minus L? Are they different? They are exactly the same. Maybe I am confused. I don't know. Okay, so the length is a property. Length is a attribute, or the metadata. Remember the keys. Remember the structure, file structure. You have a key in your record, okay? Let's say I'm a bank and I am storing my customer information in this structure, okay? And my key is my national identity number. But inside my record, I don't know where my key is. So for these kind of files, you provide the key address, key position, and key length. Also the record length too. Okay. So the creation time, time of last change, access, current size, maximum size. These are, I am not saying that these are all the file attributes that you can have. There are many more file attributes, especially for Windows. Let's open one where is, okay. This one, as you see, maybe it is difficult, a little bit difficult to see from back there. Maybe I can capture it and crop it and make it bigger that way. Maybe, yeah, it works. Did it work? Yeah, okay. So as you see, if you click on the security tab or the details tab or see, it is saying that I have versions of it. Do I have versions of it? I don't think that I have enabled that versioning thing. Let me try to, yeah, it doesn't say I have anything. Can I take a version of a file? Can I make a new version of it? Make a new version. Do you guys see it? Maybe I did not turn that versioning feature on for this file system. Yeah, see, it says that load the previous versions. But how do I make a new version? I don't know how to make a new version. Okay, so these are all properties of files for Unix. For the security, this is more detailed than Unix. Okay, I have only 3 fields in Unix: read, write, execute. This one has read, write, execute, modification, read and execute, and all of them. And I can have as many users as I have. I can say that this user can do this and that, but this user cannot. For all of them, I can do this and that. So it is more detailed. Details. Yeah, so these are the details that comes from the file itself. Since this is an image file, I can say what kind of resolution it has, okay, what kind of height and width, okay, and the bit depth of it, the color version, and etc. Anyways, the whole story is the file attributes are there. The data about your file has to be stored somewhere, and that data changes from file system to file system. Also, that data changes from sometimes depending on the file type. These are the file attributes. Okay, so let's look at some file operations a user can do on the file. Of course, I can create a file. I can delete that file. I can open and close the files. I can read, write, append, seek. I can get the attributes, set the attributes, and rename. Yeah, these are the things, okay? Let's look at these 2 operations, opening and closing, okay? I mean, why would I need to open a file or close a file? I mean, after opening a file, what do? I either read or write, right? Why don't I read a file directly? Why don't I have a function that says read a.txt a buffer, okay, read from a.txt a buffer or to a buffer like a character pointer of length 100. Why don't I have a function like that? Why do I have to open a file and then close a file? Yes?
Maybe another process reads it file.
Maybe.
Another process reads it.
Well, other processes can do the same thing too. I mean, 2 processes are doing exactly the same thing. Why should I open it?
We want to know if another process reads it, because
Well, I mean, if two different files, if two different processes open the same file, they open it in. You are saying that when two different processes open the same file, the operating system knows that it is being used by two different processes, and if they are writing to it, and if there is a race condition, then I would know it. Yeah, that's right. That would be one way of that would be one advantage of opening a file, requiring the user to open a file before using it. Yeah, that's a good point. The other thing is this, okay? You read your file to this buffer for 100 lengths, but where do you read it? It's starting from the beginning, okay? But I don't read it from the beginning all the time. I have a file pointer, and whenever I move it, it moves forward, right? So when you open a file, okay, this file is opened, you have file opening information, you know where you left after your last read. So with an open file, you can keep that kind of information. So each process, remember the process table? What do I have in a process table? Remember the process table? It says that my PID is here, okay? My permissions in my process table, my owner information, and etc. Also, in my process table, I have open files pointer, okay? So each process keeps the open file pointer, and whenever I do something about the file, okay, I keep that information in my open files field. I know where I left when I was reading that file. That's why from the beginning of the file abstraction days, we always open a file before we start using it, and we close it. Okay. Also, that makes it very possible to optimize the file reading, because when you open a file, when you read it, probably you are going to read the next bytes after your last read. So your disk reads the whole megabyte of data and puts it in a special place in your kernel or in your file library's memory. And the next time when you read it, you don't read it from the disk. You read it from the cache. Okay. So those are some of the advantages. Of course, opening files and keeping a file open means that you are using some system resource. If you open so many files, you are wasting some system resource. That's why if you don't need it, you just close your files. Okay. You are allowed to have only certain number of files open. You need to close them from time to time. Okay, so those are the file operations. We talked about get attributes and set attributes and renaming. These are the operations. I have a small program here directly from the book, a C program that copies a file from the source destination to destination. It is exactly the same as this CP, okay? t.dfg, I am going to copy it to this t2.txt. Okay, I just copied it. I have a new file now. It is exactly the same as t.dfg. So this is the program that we are going to write. This is our main function here. Buffer size is, I will read the first file block by block. My block size is this, 4 kilobytes. Okay. And my output mode, I am going to create the new file in this protection mode. It will be 0 read, write, execute, then ... and yeah. So that's how it's going to be. 7 means 111 for the user mode. So my arguments, and I have my source file descriptor, destination file descriptor, how many bytes I read from the input file, how many bytes I write to the output file. This is my character buffer. If my argument numbers, the number of arguments is not 3, then I would terminate, I would exit from this function. Okay, and this is how you open a file, right? So I'm going to open two files. One is for the read-only way, the original, the source file. The second one is the output file. Argument number 1, argument number 2. Argument number 0 is my command utility name, right? If I cannot open it, I just exit. This one, output mode, we already know it. Okay, this one is read-only. This is defined in, okay, or read-only is defined in, I think, in standard library, stdlib. It's defined in there. Okay, so, and I'm in an infinite loop. While true, I am in an infinite loop. I keep doing this in an infinite loop. I keep doing this loop. Read one block size, which is 4 kilobytes, from input file to the buffer. Okay. If read count is less than or equal to 0, that means that I couldn't read anything. That means that I hit the end of the file. In that case, I am going to break out of this loop. Otherwise, I will write whatever I had read from the input file to the output file. Out file descriptor, buffer, and read count. Okay, if the write count is less than or equal to 0, if I couldn't write anything, that means that there is a problem. Either the disk is full, or there is a mechanical problem, electronics problem with the file. I don't know. So I am going to terminate my program with this exit code. Otherwise, this loop will exit from this point. By the way, this indentation is wrong. This all has to be, so this has to be indented to the right. Okay, after that, I am going to close the in file, close the output file. If the read count is 0, the last time whatever I read is 0, that means what? That means I hit the end of file. Okay, otherwise I have a problem. I am going to exit with the signal of 5. So every time I use a different, okay, if the number of arguments is not 3, exit 1. This is my code 1. I know that. Exit 2 is if I cannot open the input file, if I cannot open the output file, here, if I cannot write to the output file, here, something else occurred. So we are letting the outside world know that what kind of problems I am having. That's it. I compile and run this program, and it becomes a very simple command, Unix utility command, CP. Of course, CP has many more command line options, such as don't copy the file data, just the attributes. Interesting. So you say, okay, this is my source, this is my destination. There is a file on destination. You are going to copy the attributes of the source to the destination. Okay. What else? Force it. I mean, even if you cannot open it, if you cannot remove it, just force it. Interactive. Every time you make a copy, just ask me. Okay. This is interesting. Did you know this? Copy -L. It is just making a link instead of copying it. Okay. You can make hard links. On that, I don't think that I knew about that. Okay. And I think there is a -R. Yeah. -R recursively copies all the directories. Okay. Copy something to something, and when you say -R, it copies all the directories recursively. It goes in there and runs this one. Okay. So remove each existing destination. Remove each existing destination file before attempting to open it. So that means that if there is something on the destination, just remove it before opening it. Okay. So that would be a good thing if the files that you are copying is too big. Okay. It looks like the default version of copy makes the file first. After the copying is done, removes the destination and renames the created file. But that means that you need lots of space for that. If the files are large, then that's going to fail. But this one says that before creating your destination file, just remove the destination first. So this one is symbolically, and okay, good. So I mean, what I meant is, of course, the Unix CP is much more complicated than that. For this one, I don't have any command line switches. Okay, implementation of those command line switches would be, well, it is not difficult, but it will take time. And this program will not be like 50 lines of long. It will be a few thousand lines long. Okay, good. Any questions? No questions. So directories, again, special files. To keep track of files, file system normally have directories or folders, and they are files. Actually, you see that, right? When I say, give me all the files here, it says, okay, some of them are hidden files. This one is a special file, it's a directory file. This one is a directory. How do I know that? Because there is a D in front of them. Okay, there is a D in front of them. So if you like to see what is in a directory file, you have this utility, right? CD. You will say go there, CPP test. Now this will be my working directory. Print working directory. My working directory is there, CPP test. Previously, my working directory is home Akgül. Now I have CPP test. Okay, my working directory is CPP test under my home directory. I am in a different directory, and when I say list all the files, it lists them. Okay. Okay, so there are many files in there, and I can see the directory. I can see their properties and everything, right? Okay, and inside this directory, there are other directories like this chapter 1 or Onur. Okay, so that's the meaning of a directory. It's a special file. It keeps files in it. Of course, this file, this directory file, what is the size of a directory? Okay, what is the size of a directory? Let's go back. Let's look at the CPP test. Size is not that big, right? It is just 4 kilobytes. But inside it, there are many files. You would say that how come the size of that directory is not that big? Well, this directory only contains the file information. It doesn't contain the file themselves. Okay, it just contains the file information. Okay, so you don't expect this number to be very, very large. Okay, you don't expect it to be very, very large. If I go there, CPP, okay, CPP test, and how do I make all these files? How do I make lots of files? I don't know. How do I make them? I like to copy them, and maybe I can do this. Yeah, I can do this. I am going to explorer.exe. I am going to use the, okay, so take all of these files and copy and paste. So I am pasting them. So the number of files I have increased by 2. I just copied them. I am pasting them again. So the number of files are going to be much larger than before. So how many files do I have now? How do I ls tell me how many? Okay, maybe I should do this wc minus l. Total of 100 files. when I go back up, when I do this, see, well, it still didn't increase anything. Okay, so that means what? That means I have to add many more files to increase this, because this 496, it is not by coincidence, it's 4 kilobytes, right? So certain number of files I can add them without making this file larger. But I don't think that this is going to stay like this forever. If I add enough number of files in it, this number will increase to maybe 8 kilobytes. But it will not be very, very large like these files. Okay. So for example, if I move this my.tar file to CPP test, I moved it. Now CPP test has this large tar file in it, but the size of the CPP test didn't change because I have only changed it just a little bit inside my CPP test directory. Okay, so again, those are directories. Sometimes they are called folders. Okay, they are files, but they are special files. At the beginning, for example, in the second generation computers, you had only one directory. Okay, so you had to store all of your files in the same place. So each file has to have a different name. And it looks like they didn't have multitasking or time sharing in those days, which is right. Okay, so whoever got the computer first, okay, they can use this, so they can do whatever with the root directory. And on early personal computers in 1970s, okay, they had a structure like that. The computers, those microcomputers, they were so primitive that only a single directory is available, the root directory. Okay, single level directories. Nowadays we don't have this kind of directory structure. Nowadays we have this. There is this root directory under the root directory. Maybe the files for the user A, user B, and user C. Under user A we have, or user B, we have other files, and each user can have their own directories. Under directories, they have their own files. This is the hierarchy of the directory systems. Okay, so we already know that from our Unix or from our Windows operating systems. Of course, with this kind of system, we have the issue of the path names. For example, the CPP test, and when I say ls, I don't know what. Okay, ls test.exe, ls minus al. I'm trying to get the full path for this test.exe. I guess I will do that. Okay, what is my current working directory? It is this directory. Under this directory, there is this test.exe. Okay, this is my full path. Okay, if I like to copy a file giving this from home to my test.exe, I am going to copy this file. I gave this full path, and I am going to copy it to this directory, tmp, if I have it. It looks like I don't have such a directory. What do I have at the... No? Well, yeah. Well, what does it say? Oh, it says test. It is test.txt, right? Yeah, okay. So it copied it. So I gave this full path as the source file to some destination file, and it just worked. And in fact, I could do this hs data, and yeah, see, I can copy from any part of my system to any other part of my system with the copy command. No problem, it works. So these are called absolute path addresses. Starting from the root, I can go all the way to my file, and I can specify the positions on my file system. That way, that's one way of specifying the path names. That's called the absolute path names. Okay, each file is given an absolute path name consisting of the path from the root directory to the file. The other type of path names is the relative path names. Okay, relative path names. For example, here, instead of doing this cpp, okay, go to that directory. My current working directory is this. I can say copy test.exe. So I am not giving the full path, I am giving the relative path, or maybe I should do it this way. Maybe this is better. Okay. So copy from cpp test to test.exe here. Copy something under cpp test.exe to this working directory. Okay, and it will work. So this is called relative path names. I am giving these path names relative to my current working directory. This is my current working directory, pwd. Okay, and the way to change the current working directory is the change directory command, right? I change my working directory by doing this, or I change my working directory by doing this. Okay, this is my working directory. I don't know what kind of things, I don't have much. Okay, so these are kind of standard between the popular operating systems, and most of them, they come from, most of these notations, it comes from where? From Unix, and Unix comes from Multics, of course. So Multics has specified in 1970s and 60s that the paths are going to be specified this way, using these angled brackets. Okay, later Unix changed these angled brackets to slashes, and Windows and DOS changed those slashes to backslashes. Okay, probably a bad decision. These backslashes are problematic because for Unix, for C, backslash means that something special is coming, right? Special character like backslash n, backslash p, etc. For the Unix, the slash is a better choice. So we have these kind of structures for modern operating systems. Okay, some people don't like this idea. I mean, if for example, if this file named dictionary, dict, okay, if it belongs to this library, then you will say that, I mean, why do I have to belong to a single directory? I mean, I am a file. I like to belong to both this library directory. Also, I like to belong to this etc. etc. directory here. Okay, why can't I do that? I mean, why do I have to have a single owner as a directory? And the answer is, well, our structure is like that. Some operating systems said that no, I can have many directories, and these directories, and I can be involved in many directories, and these directories will be in my property list. They said that, but this kind of structure doesn't make it impossible to have such a structure, because we have this nice feature of linking. Let me go to my home directory. In my home directory, instead of, let me remove that test.txt, okay, instead of copying that test.exe, I am going to link it. Link my source cpp test.exe to here. So I did not copy it, I just linked it. So both cpp test and my current directory, they show this test.exe. okay, test.exe as my file in my directory. And in fact, this test.exe is shared between these two directories. Okay, linking is one way of sharing files between the directories. So it's going to be, for example, this dict, right? Dict will be, okay, so it will be somewhere in the desk, okay, because lib is a directory. It contains the names and the pointers of these files. This is the dictionary file, and if I like to include this file in another directory, then I can do this. This is linking, okay? So I did a linking of this file dictionary, okay, by giving this command ln command. Okay, it looks like I don't see anything that shows that this test.exe is a well, I have it here. I have it cpp test.exe on both of them. It is exactly the same thing, okay, and I am not seeing any indications of these are the same things. I mean, they are not copies, they are the same things. If I try to remove, let's say, cpp test.exe, I removed it, so this will say I don't find it, but this will say it is here. Okay, so I mean, they are linked, but removing one of them will not remove the actual file. Removing them will not actually remove the actual file. Let me go to ls and try to see what kind of option should I give you to get the linked files. Hyperlink file names. What? Next. Dereference -L. Dereference link. When showing file formation for a symbolic link, showing information for the file. -L. Let's try this one. Maybe do I have it? But I don't have the link anymore. Anyway, you try it. Try to understand which files are linked and which files are not linked. When I do this, see, this one is a linked file. I know that, but this is not a hard link. This is a symbolic link. And I will talk about the hard links and the symbolic links tomorrow. I already know that because, see, there's an L sign in there. This is a linked file. But I don't know how to see that for a hard linked file, not the soft link one. We are going to look at it tomorrow. It looks like I'm out of time. I will stop at this point and I will continue tomorrow. Okay, thank you.